Welcome to the AI Coach by Anil Nathu.
Have you ever felt that familiar frustration? You're staring at a sprawling spreadsheet packed with thousands of rows and columns, and genuinely,
Hmm.
you just don't know where to even begin to extract meaningful
Oh,
insights.
absolutely. I think we've all been there.
You are absolutely not alone. Tabular data, that ubiquitous format we see everywhere, right? From critical business reports to complex scientific studies, it holds immense potential.
Huge potential.
But unlocking that potential, transforming raw numbers into actionable understanding, well, it can often feel like trying to navigate a vast, dense forest without any reliable map or compass. It's tough.
It really is. You just get lost in the weeds sometimes.
In this deep dive, we're going to pull back the curtain on a groundbreaking new framework called TablePilot. Now, this isn't merely about accelerating number crunching.
No, it's much more than that.
It's about making data analysis remarkably intelligent, incredibly diverse, and surprisingly intuitive, all powered by the transformative capabilities of large language models.
Our mission today is to show you precisely how artificial intelligence can cut through that complexity, uncover hidden patterns you might never spot on your own, and deliver insights that truly resonate with human understanding and priorities.
Getting to what actually matters.
Exactly. We'll delve into compelling real-world examples, explore the fascinating mechanics of how this technology operates, and discover the practical applications that promise to fundamentally reshape how you interact with data in your professional and personal life.
Yeah, this could really change things for a lot of people.
Our journey today is guided by a cutting-edge research paper titled TablePilot, recommending human-preferred tabular data analysis with large language models. This impressive work comes from a collaborative effort. Brilliant minds like Dain Yi and their colleagues at prestigious institutions. We're talking Shanghai University of Finance and Economics, Peking University, the University of Illinois Urbana-Champaign, and Microsoft Research.
Quite a lineup.
Definitely. You can actually access this paper yourself on arc5e.org. The identifier is 2503.13262. And we believe it truly lays out a new paradigm for interacting with complex data.
It really does set a new standard, I think.
Okay, let's face it, tabular data can be intimidating. We've all stared at a massive spreadsheet, whether it's sales figures, scientific measurements, financial records, and just wondered, where do I even begin?
The blank slate problem.
The paper touches on its inherent complexity and density, citing previous research. From your perspective, beyond just the sheer volume, what exactly makes this type of data so uniquely challenging for us humans to analyze effectively?
That's a great question because it gets right to the core of the problem TablePilot aims to solve. The challenge isn't just about processing large volumes of data, although that's certainly a hurdle.
Right.
What's truly fascinating here, and maybe a bit counterintuitive, is that even for seasoned professional analysts, the initial step, just figuring out the most appropriate operations to perform on a new table, can be incredibly tedious.
So not just finding the answer, but finding the question.
Exactly. You're often not simply looking for a specific answer, but the right questions to ask the data in the first place.
Okay.
Imagine you're handed an airport's passenger traffic report. This isn't just a simple list. It could span decades, include data from dozens of major U.S. airports, break down passenger types, domestic, international, categorized by month, year.
It gets complicated fast.
Super fast. Without an initial direction, how do you even begin to identify the top performing routes or detect subtle seasonal trends that impact staffing or accurately forecast growth patterns for future infrastructure planning?
Right. There's so many possibilities.
The sheer number of possible analytical paths, filtering, sorting, grouping, charting, statistical modeling, quickly becomes overwhelming, and the stakes are genuinely high. Errors or missed insights here can lead to suboptimal outcomes, as the authors rightly point out. Whether that's misallocating resources, making poor investment decisions, or drawing incorrect scientific conclusions.
Yeah.
It's like being given all the ingredients for a gourmet meal, but no recipe, no idea what kind of dish you even want to make, and 100 different ways to combine them. The cognitive load is just immense.
Okay, that makes sense. Now, we've certainly seen traditional machine learning methods do amazing things with recommendation systems elsewhere. Product recommendations, movie suggestions.
Yeah, they're everywhere.
So what makes tabular data analysis so different? Why do those established methods fall short here? Is it the variety of data or something more fundamental?
It's a bit of both, but I think it primarily comes down to a fundamental limitation. The paper makes a very clear distinction here. Traditional machine learning approaches, while incredibly useful in specific contexts, they often suffer from Poor generalization ability, suboptimal performance, and a strong dependence on specific data sets.
Okay, what does that mean in practice?
Well, it means they tend to be highly specialized. If you train a model to recommend analysis for, say, a very specific type of financial transaction data, it might perform brilliantly there. But then if you present it with medical patient records or climate data, or even just a slightly different format of financial data, its performance plummets.
So they don't adapt well.
Exactly. They struggle to adapt to new, unseen data structures or novel analytical contexts without significant retraining. And that lack of adaptability is a huge bottleneck in real-world data analysis, where every new data set often presents unique challenges.
Right.
This is precisely where modern adaptable tools found in platforms like, say, AI Coach by Anil Nathu offer a distinct advantage. They're designed to handle a wider variety of data types and analytical needs without requiring complete re-engineering every time. They learn more generalizable patterns, making them far more flexible.
So this is where large language models, LLMs, come into the picture. They've certainly made waves recently, revolutionizing fields from creative writing to customer service. When you think about their capabilities, like understanding natural language, even generating code, it seems like they'd be a natural fit for data analysis. So what are the opportunities they open up here? And maybe more importantly, what were the biggest hurdles the researchers, Dani and colleagues, faced in getting them to work effectively in this specific domain?
You've hit on a critical point there. LLMs do offer tremendous potential. They have strong data processing, language understanding, and generation capabilities. This means they can interpret complex natural language queries, grasp context from textual descriptions of data, and even write the Python code needed to execute analytical tasks. These are incredibly valuable skills for automating and democratizing data analysis.
Okay, so the potential is there. What are the roadblocks?
Right. However, the authors pinpoint 3 significant challenges that prevent just, straightforward application of general-purpose LLMs to complex tabular data analysis. Challenge number 1, data intensity and hallucinations. Tabular data, as we've established, can be absolutely massive. Millions of rows, hundreds of columns sometimes.
Right.
While LLMs are powerful, they have limitations in their context window. That's the amount of information they can effectively see and process at once. Trying to feed an entire sprawling data set directly into an LLM can overwhelm it.
Too much information.
Exactly. When the context window gets too long or too densely packed, it significantly increases the risk of inaccurate results, or what we commonly call hallucinations. The model might start generating plausible-sounding but factually incorrect information because it's struggling to maintain coherence across all that input.
Like it's guessing, almost.
Sort of. It's like trying to remember every single detail from a 1,000-page book simultaneously. Some facts are bound to get muddled or even invented.
Okay, challenge 1, size and hallucinations. What's next?
Challenge number 2, lack of diversity. Many existing LLM approaches, especially earlier ones, tend to focus on generating a single type of operation or executing predefined data analysis queries.
Yeah.
Meaning, if you ask an LLM about your sales data, you might get a total sales figure, but it might not spontaneously suggest, say, a quarterly trend chart or a geographical breakdown or a statistical projection for next year.
So too narrow.
Right. A truly useful data analysis recommendation system needs to offer a wide range of analytical perspectives, basic filtering, complex visualizations, advanced statistical modeling to provide a comprehensive holistic view, not just a narrow slice. This diversity is crucial for discovering multifaceted insights.
Got it. Diversity is key. And the third challenge?
And then there's challenge number 3, human preference alignment. This is arguably the most critical one for real-world application. It's one thing for an AI to generate technically correct code and results, that's step 1. But it's another entirely to ensure that the recommended analysis is not just accurate, but also meaningful, insightful, interpretable, and critically aligns with human cognitive patterns.
How we actually think.
Precisely. As discussed in related research, a machine might find a statistically valid correlation, but if that correlation is trivial or obvious or presented in a way that's impossible to understand, it's virtually useless to a human analyst trying to make a decision.
Right, it has to be useful.
Exactly. The ultimate goal is to provide insights that truly resonate with how people actually think about, understand, and apply data in practical scenarios. It's about utility, not just raw output.
That's a really comprehensive breakdown of the hurdles. So how does TablePilot manage to tackle these significant challenges? the data intensity, the need for diversity, and that crucial human preference alignment. The paper introduces it as a pioneering tabular data analysis framework, leveraging large language models to autonomously generate comprehensive and superior analytical results. That sounds incredibly sophisticated.
It really is, and TablePilot is specifically designed for what they call zero-turn scenarios, which is a key differentiator.
Zero turn. What does that mean?
It means it works effectively even when there's no previous user history, no profile, no prior interactions to draw from. It doesn't need to learn your specific habits over time.
Okay. It works right out of the box, essentially.
Exactly. It can infer what's important directly from the data itself and general human analytical processes. Its core output for any analysis task is structured as query code result triplets. That's the natural language question it formulates, the Python code it generates to answer it, and the actual findings derived from that code. It's a very structured, repeatable approach.
Query code result. Okay.
Let's break down its elegant four-step process. It's illustrated really well in Figure 2 of their paper. This systematic approach is really at the heart of why a platform leveraging this kind of AI, like AI Coach by Enil Nathu, can be so effective and reliable for different kinds of users.
Okay, let's do it. Step 1.
First up is analysis preparation.
Right. Before you can dive deep into any data, you need to make sure your raw information is in the best possible shape for the AI to understand and process efficiently. From a practical standpoint, what exactly happens in this crucial first step?
This step, as meticulously outlined by Yi and colleagues, is absolutely foundational. It's critical for both the efficiency and, importantly, the accuracy of everything that follows. It involves two key tasks designed to transform that raw, potentially massive tabular data into something more focused, digestible, and semantically interpretable for the LLM.
Okay, 2 tasks. What's the first one?
The first task is table sampling. Raw tables, especially in the real world, can be enormous, right? Millions of rows, hundreds of columns.
And establish that, yeah.
Trying to feed an entire unedited data set like that directly into an LLM is, as we discussed, highly problematic. Context window limitations, risk of hallucination.
Right.
So TablePilot addresses this head-on. It employs sampling techniques, drawing on established methods from other research. Think of it like this. Imagine you're an art critic trying to understand a huge, intricate mural. You wouldn't press your nose right up against it and scrutinize every single brushstroke all at once, would you?
No, you'd step back.
Exactly. You'd step back, maybe take a well-chosen snapshot of the whole thing, or zoom in on key sections that look representative. That's what table sampling does. It extracts a statistically representative subset of the original data.
So it shrinks it down, but keeps the important characteristics.
Precisely. This significantly reduces the computational load on the LLM, makes the input more manageable, and helps focus its attention. This helps mitigate those long context window hallucination issues we talked about. For instance, in their airport passenger data case study, that's Figure 4, the original table is massive, spanning decades and many airports. TablePilot intelligently samples this data to represent its overall structure. The types of data it contains, like airport code, year, passengers, etc., and the general patterns, without needing to process every single entry. This initial reduction helps the AI grasp the essence of the table without getting bogged down.
Okay, sampling first. What's the second task in preparation?
The second, and equally vital task, is table explanation. This is where TablePilot enriches the sampled data with critical human-like context. It dynamically generates a table explanation, which they call E in their framework.
An explanation, like notes.
Sort of, but much more structured. This explanation includes the table's overall theme, highly detailed descriptions for each column, and crucial relationships between columns. The paper explicitly states this process incorporates world knowledge learned during the pre-training phase of LLMs.
Wow. So it's using its general knowledge, too.
Yes. Think of it as giving the AI a comprehensive semantic briefing, going way beyond just the raw data point.
Can you give an example, like from the airport data?
Absolutely. Let's zoom in on Figure 4 again, the annual and monthly passenger traffic statistics table. For this table, TablePilot's explanation function would detail things like table theme, clearly defining it as annual and monthly passenger traffic statistics for major U.S. airports. Sets the context immediately. Column descriptions. Each column, airport code, year, month, domestic passengers, international passengers, total passengers, gets a specific readable description. For example, total passengers isn't just a number. It's defined as the sum of domestic and international passengers, a key metric for assessing the total passenger throughput. This helps the LLM understand the meaning, the semantics. Column relationships. This is where it gets really smart. The explanation clarifies how airport code links to everything else, enabling airport-specific analysis. It states how year and month create a time frame, suggesting time series analysis. And crucially, it highlights that domestic passengers and international passengers contribute to total passengers, explaining the calculation.
Ah, so it understands the total domestic plus international.
Exactly. And that prevents the AI from, say, foolishly trying to predict total passengers from domestic and international as if they were independent drivers. It understands the inherent dependency.
That deep contextualization in the preparation phase sounds incredibly insightful. It really feels like TablePilot is building a rich mental model of the data rather than just treating it as a flat file.
That's a great way to put it.
Getting this initial groundwork right must prevent massive headaches later on. How often do you see real-world issues pop up just because this fundamental stuff isn't done properly?
Oh, it's shockingly frequent. Many analytical errors or just, weak insights don't come from faulty calculations later on. They come from a fundamental misunderstanding or a lack of clarity about the data itself right at the start. If you misinterpret what a column means, or you miss a crucial relationship between variables, any analysis you do after that, no matter how technically correct the math is, will be flawed or misleading.
Garbage in, garbage out, basically.
Pretty much. This preparation phase is a critical lesson for any data analysis. Whether you're using a sophisticated AI like TablePilot or doing it manually in Excel, understanding your data structure and meaning up front saves immense time, prevents misinterpretations, and ensures your insights are actually grounded in reality. It's the difference between blindly crunching numbers and genuinely understanding the story your data is trying to tell.
Okay, so once that data is so thoroughly prepared and understood, TablePilot moves into the next phase, module-based analysis. This sounds like where the real action happens, generating those diverse insights. What exactly are these modules, and what kinds of questions or insights are they designed to deliver?
Right. This step is all about achieving that comprehensive coverage of analysis tasks we talked about earlier. It uses a clever modular design. The framework autonomously generates those query code pairs, the question and the code to answer it, for 3 distinct but complementary types of analysis. This is why you get such a holistic, multifaceted view.
3 modules. What's the first one?
First, we have the basic analysis module, MBA.
Okay, basic sounds. Well, basic.
Well, yes and no. The operations are fundamental but incredibly powerful. Think of the core things you do to quickly summarize, filter, or reorganize data. This module is about getting to key summary data or isolating specific subsets efficiently.
Like filtering and sorting.
Exactly. And grouping, aggregation. The paper gives good examples in Figure 5. Filtering, like filter the data to show only the records for the airport code JFK. Simple, but essential to focus. Sorting. Sort the data by total passengers in descending order. Instantly shows you the busiest entries. Grouping and aggregation. Maybe group the data by year and calculate the total number of domestic passengers for each year. Reveals yearly trends quickly. Pivot table. Even something like create a pivot table to show the total number of international passengers for each airport code and year. That gives you multi-dimensional summaries.
Okay, so the foundational stuff. Got it. Module 2.
Next up is the data visualization module, MDV.
Ah, the charts.
Exactly. This module is dedicated to generating compelling visual representations of data. The goal here is to reveal patterns, trends, relationships, outliers, things that might be completely hidden in raw numbers.
A picture's worth 1,000 words.
Or 1,000 rows in this case. A good chart can tell a complex story almost instantly. The paper shows examples like line chart. Generate a line chart to show the trend of total passengers over the years for each airport. Vital for seeing change over time. We'll see examples later in Figures 7, 8, and 10. Bar chart. Create a bar chart to compare the number of domestic and international passengers for each airport. Great for direct comparisons. Figure 6 has one. Pie chart. Create a pie chart to show the proportion of total passengers for each airport. Good for part-to-whole understanding. Stacked bar chart. Generate a stacked bar chart to show the relative trend of domestic passengers and international passengers for all airports. Figure 10 uses this powerfully to show the composition changing over time, like that internationalization trend.
Okay, basic analysis. Data is what's the third module?
Finally, we get into the statistical modeling module.
So going beyond just describing the data.
Exactly. This module applies more advanced statistical techniques. Think regression analysis, hypothesis testing, predictive modeling. This is where you start to understand not just what happened, but maybe why it happened and what might happen next.
Okay, like forecasting.
Precisely. Examples from Figure 6 include trend prediction. Perform a trend prediction analysis to forecast the total number of passengers for the next 12 months at JFK Airport using historical data. Super critical for planning. Figure 11 shows this kind of forecast. Correlation test. Conduct a correlation test to determine the relationship between domestic and international passengers. Reveals dependencies. Regression model. Build a regression model to predict the total number of passengers based on the number of domestic and international passengers. Figure 6 shows regression results. Although, as we'll see, TablePilot is smart enough to flag when a model like this, even if technically correct, is actually meaningless.
Interesting. We'll come back to that. This modular approach sounds incredibly powerful. It means you get a truly holistic, multi-dimensional view without having to think through every single possibility yourself.
Right.
It's like having a whole team of specialized data scientists, one for basics, one for visuals, one for stats working together for you. This is the kind of intelligent assistance you'd expect from a sophisticated AI platform like AI Coach by Anil Nathu.
It covers the bases automatically.
So TablePilot generates these query code pairs across its modules, producing this wide array of potential insights. But is it always perfect on the first try? I mean, does it just spit out code and hope for the best?
No, definitely not. And that leads us to the next crucial step. Analysis optimization.
Optimization. Okay, so it refines its own work.
It absolutely does. This step is TablePilot's built-in quality control, and it's crucial for ensuring the results are not just correct, but also accurate and meaningful. The process starts by actually executing the Python code generated by the analysis modules to get a result.
Okay, it runs the code. What happens then?
Well, two things can happen. The code might error out a bug, basically, or the code might run successfully, but the result itself isn't great. Maybe it's a chart with overlapping labels, or the insight is just trivial.
Right.
TablePilot has different optimization paths for these. Optimize B handles the code errors, debugging, and fixing. Optimize A handles the cases where the code runs, but the result needs improvement. This dual-path approach ensures it can fix both functional bugs and qualitative issues.
How does it actually improve things?
The core of this optimization involves refinement with LLMs. The large language models are used not just to fix broken code, but to actively improve the alignment of the query and the code with the data and the analysis intent. It's about enhancing the insight itself.
Can you give an example of that?
Yes, one of the standout features is the multimodal revision module. This is where the AI demonstrates it can see and interpret visual outputs.
See the charts.
Yeah. The paper gives a great example in Figure 7 and 8. An original line chart query tried to show the trend of total passengers over the years for each airport, but the result in Figure 7 was a mess. Overlapping y-axis labels, data labels overlap. It was just unclear.
I've definitely made charts like that myself.
Well, we all have.
Yeah.
But TablePilot's multimodal revision module can actually recognize unclear images from that output. It processes the visual, sees the clutter, and then revises the underlying code to fix it.
Oh.
The paper even quotes the improvement reason the AI generated. The original code suffers from overlapping y-axis labels. I pivot the data. This approach avoids label overlap. Additionally, the chart is improved by automatically handling missing values and using tight layout. The optimized result in Figure 8 is dramatically clearer, legible, actionable. It shows real visual understanding.
That's amazing. It fixes bad charts automatically. Does it optimize the content too, like the insight itself?
Yes, absolutely. It also performs content optimization. And there's another example from Figure 7. An original query was to filter the data from 2000 onwards and sort by total passengers. Kind of basic.
Okay.
The model flagged this as somewhat redundant and not very insightful. The improvement reason explained. It's important to notice that the total number of passengers has been increasing. To enhance the analysis, I will add a new column that represents the year-over-year growth rate.
Ah, much more insightful.
Exactly. The optimized query became calculate the year-over-year growth rate, allowing insights into the changes in passenger volume over time. It transformed a trivial filter into a much more valuable analysis, showing the dynamics of change.
That's truly remarkable. This optimization step really highlights the iterative nature of good data analysis. TablePilot doesn't just generate. It critiques and improves its own output. It means you get not just answer, but a better answer, often anticipating the next logical question. This continuous refinement is surely a cornerstone of a valuable AI assistant, like the capabilities within AI Coach by Anil Nathu.
Definitely. It elevates the quality significantly.
So after all that meticulous generation and optimization across the modules, TablePilot has potentially produced quite a few insights. How does it decide which ones to actually recommend to the user? This is where analysis ranking comes in, right? And the paper introduces this method called Rec-Align. What's the secret sauce here? How does it ensure the recommendations align with what we find useful?
Right. This final step is all about ensuring the insights presented are truly human preferred. The goal is to evaluate and rank all those refined query code result triplets that came out of the optimization step. And the ranking isn't just about technical correctness.
It's about usefulness.
Exactly. It's a holistic assessment based on multiple dimensions that capture what's useful, interpretable, and meaningful to a human analyst in a real-world context.
Okay, what are these dimensions? How does it judge them?
The paper, especially in Appendix E, details 6 explicit criteria the LLM uses to score each triplet. Think of it as a rubric for human-centric analysis. Meaningfulness. Does it provide actionable insights? Does it help answer a real question or support a decision? Like that passenger forecast, highly meaningful. Relevance. How closely does it align with the dataset's core topic? For airport data, queries about passenger traffic are highly relevant. Reasonableness. Does it follow sound data analysis principles? Does it make logical sense for this data? Grouping by airport code and averaging passengers, that's reasonable. Diversity. Does the set of recommendations cover a good range of analysis types? Not just 5 bar charts, but a mix of tables, chart, maybe a stat model. Interpretable. Is the output clear and easy to understand? Is the chart well labeled? Is the query unambiguous? That multimodal revision helps here. Insightfulness. Does it reveal something new or non-trivial? Does it go beyond the surface? Calculating year-over-year growth is generally more insightful than a simple filter.
Wow, that's quite comprehensive. Meaningful, relevant, reasonable, diverse, interpretable, insightful.
It really covers the basis of what makes analysis good from a human perspective. And the paper highlights that Rec-Align is implemented using Direct Preference Optimisation, or DPO.
DPO? What's that?
It's a powerful technique that tunes LLMs directly from human preference data. Instead of the AI trying to guess what humans want, it learns directly from examples of preferred versus less preferred outcomes.
So it learns from feedback like, this chart is better than that one.
Precisely. This ensures the model effectively selects responses that are better matched to human values, increasing the recall of value-aligned outputs. It's learning what feels right and is most useful to a human analyst.
Can you show how this ranking works in practice? Any examples?
Sure. Figure 9 in the paper gives some great examples. High-score queries included things like group by airport code, calculate the average domestic passengers, and sort. That got top marks 5s for meaningful, relevance, reasonableness. Makes sense, right? It's useful, relevant, logical.
Yep.
Another high score was create a line chart to analyze the trend of total passengers over the years. Again, high marks for meaningfulness and insightfulness because it visualizes trends.
Okay, those seem like good recommendations. What about low-scoring ones?
This is where it gets really interesting. Remember that regression model query? Build a regression model to predict total passengers based on domestic and international passengers.
Yeah, the one that seems statistically perfect but maybe wasn't useful.
Exactly. TablePilot gave that a low score, just 2 for meaningful. And the reason it provided is incredibly revealing. While the regression model shows a perfect fit, r² equals 1.00, the analysis is meaningless because the total number of passengers is simply the sum of domestic and international passengers, making the model redundant.
Wow, so it caught the logical fallacy.
It did. It demonstrates this profound ability to identify not just technically correct, but truly meaningful and non-trivial analyses. It avoids redundant or misleading insights that might just waste an analyst's time. It's flagging an analytical trap.
That's a huge time saver, flagging a technically perfect but ultimately meaningless model. Why is that kind of semantic intelligence so critical in real-world analysis? How does it prevent common mistakes?
It's absolutely critical, and it addresses a major blind spot in purely statistical automated analysis. In the past, an algorithm might churn out that statistically perfect regression, and an analyst, especially someone new to the dataset, might spend ages trying to interpret its supposed insights, right?
Chasing ghosts, almost.
Exactly. TablePilot's semantic intelligence, which comes from understanding those column relationships back in the preparation phase and gets refined by the DPO ranking, allows it to go beyond just statistical correlation. It grasps the logical relationships. It knows total passengers is derived from the others.
So it avoids those logical traps.
Right. It prevents that common pitfall where analysts might prioritize a shiny statistical metric like a high R squared over actual practical meaning. Without this semantic layer, you could build all sorts of complex models that just describe arithmetic truths instead of uncovering genuinely new causal or predictive relationships. TablePilot acts like a guardrail. It ensures the recommendations are not just computationally sound, but also inherently valuable and non-trivial. It nudges analysts towards asking truly insightful questions, rather than just confirming what's already obvious from the data definition.
This is where TablePilot truly shines for you, the listener, the learner. You're not just getting raw data or random charts. You're getting a curated, ranked list of the most impactful and easiest to understand insights, rigorously optimized for human comprehension.
Getting you to the aha moment faster.
Exactly. And knowing that insight is actually meaningful.
So how do the researchers train this incredibly intelligent system to be so discerning, to align so well with human preferences? What goes into building this? The training process for TablePilot is quite sophisticated. It's a multi-layered approach designed to ensure both raw accuracy and that deep human alignment. It primarily relies on two key techniques: Supervised Fine-Tuning, or SFT, and that Direct Preference Optimization, or DPO we just talked about.
Okay, SFT and DPO, how do they work here?
First, they use analysis SFT. This focuses on training the LLMs within each of those analysis modules: basic, data viz, stat modeling. The goal here is to make these LLMs really good at following instructions, generating relevant queries, and accurate code.
So getting the basics right, making sure the code works.
Precisely. Building that foundational capability and reliability. If it needs to do an aggregation, SFT ensures it generates the correct Python code for that specific task.
Got it. What about rank SFT?
Rank SFT fine-tunes the ranking module itself. It trains the LLM in the rank component to better follow instructions in evaluating each analysis triplet based on comprehensive criteria and assigning appropriate scores. So it learns to consistently and accurately apply those 6 human-centric criteria: meaningfulness, relevance, etc., when scoring the outputs.
Teaching it what good analysis looks like.
Exactly. Teaching the AI what a good recommendation looks like from a human viewpoint.
And then DPO comes in.
Right. The final and arguably game-changing piece is Rank DPO, which implements their rec-align method. As we discussed, DPO refines the ranking by directly incorporating human preferences. The paper emphasizes this, further enhances the quality of the recommended analysis by ensuring the evaluation and scoring are more closely aligned with human analytical preferences.
Learning directly from human feedback.
Yes. It learns from actual human examples of what's preferred versus what's not. DPO learns directly from these comparisons, allowing the model to internalize the nuanced qualitative aspects that make an analysis truly valuable to a person. It ensures outputs are not just functional, but genuinely valuable and intuitive.
This multi-layered training really explains why a tool like AI Coach by Anil Nathu can feel so robust and trustworthy. It's not just raw power, it's carefully sculpted power, designed to be truly helpful and intuitive.
It's about building that alignment.
Okay, theory and training are great, but the proof is always in the pudding, right? The paper presents extensive experiments to validate TablePilot's effectiveness. What exactly did Dayini and the team test, and what were the key results? Did it actually work better?
They conducted a very thorough evaluation across those 3 core analysis tasks: basic, data viz, and stats modeling. And to do this properly, they developed and used a custom-curated dataset they call DART, Data Analysis Recommendation for Tables.
DART.
Yeah, and this is a significant contribution itself, as it's the first dataset specifically designed for this kind of comprehensive recommendation task, filling a gap in the research.
How did they measure success?
They used key metrics. For code quality and stability, they measured execution rate, execrate, how often the code runs without error. Crucial, right?
Absolutely.
For recommendation quality, they used recall at K, recall at all, recall at 5, recall at 3, basically, is the best or preferred result in the top K recommendations. For the statistical tasks, they had specific success criteria like MAPE for regression, p-value for correlation, R-squared for forecasting, to ensure the results were statistically sound.
What models did they test it on?
They used state-of-the-art vision language models, the powerful GPT-4o, the smaller GPT-4o mini, and the open-source Phi-3.5-Vision, chosen for their ability to handle both text and images, key for that multimodal revision.
And the results? Did TablePilot improve things?
Yes, significantly. Looking at tables 1 and 2 in the paper, TablePilot, even in its vanilla form, meaning without specific fine-tuning, just the framework itself consistently delivered substantial performance improvements across various models compared to the baselines.
So the framework itself is effective.
Highly effective. GPT-4o saw consistent gains across the board. But what's really encouraging is that the smaller models, GPT-4o Mini and Phi-3.5-Vision, also achieved significant gains. Their overall recall went up by 16% and 13% respectively. And their execution rates, code reliability, saw up to a 50% boost, especially in the modeling tasks.
Wow, a 50% boost in code working? That's huge for smaller models.
It's massive. It shows TablePilot enhances both relevance and reliability, even on less powerful LLMs.
What about the fine-tuning? Did that help further?
Oh yes, the impact of tuning was very clear. Supervised Fine-Tuning, SFT, significantly improved both analysis generation and ranking. And when vision-enabled SFT was combined with DPO, that rec-align method, it further boosted ranking performance, really locking in that human preference alignment.
How much improvement?
While GPT-4o saw modest gains over vanilla after tuning, the smaller models really benefited. GPT-4 Mini improved by 10–20% on average in recall. Phi-3.5-Vision showed the most notable improvement, exceeding 20% on average, with recall at N increasing by 26%.
So tuning is critical, especially for smaller models.
Absolutely. These results unequivocally highlight the critical role of fine-tuning in optimizing TablePilot, ensuring greater alignment with human values and making it powerful even on more constrained systems.
These results really drive home that TablePilot isn't just a concept. It delivers tangible, measurable improvements. It suggests AI-driven data analysis is becoming a truly reliable tool.
Moving from promise to practice. Yeah.
Okay, numbers and metrics are one thing, but how did actual human data analysts perceive TablePilot's recommendations? Did it feel right to the experts? Was it genuinely useful beyond the stats?
That's the million-dollar question, isn't it? And yes, they tested this directly. They conducted a rigorous human evaluation on 300 unseen test tables. They compared the baseline model, TablePilot Vanilla, no tuning, and TablePilot Tuned.
How did they do it?
They brought in 5 experienced data analysts. Crucially, these analysts worked under randomized blind selection protocols. They didn't know which system generated which output, preventing bias.
Smart. What was the judging?
They scored the results based on criteria that human experts really value. Practicality. Was it relevant and useful for real-world tasks? Clarity. Was the query unambiguous? Was the result easy to interpret? Insightfulness. Did it provide meaningful, non-trivial insights? Did it reveal something new?
Okay, practicality, clarity, insightfulness. Rated 1 to 5.
Exactly. Higher scores are better. And the results, shown in Table 3, were really compelling. TablePilot Tuned consistently outperformed other models.
How much better?
It achieved the highest mean score, 4.11, a significant jump from the baseline's 3.11. Even more importantly, it had the largest share of high-rated outputs, scores of 5, 4, 3, and crucially, the lowest share of low-rated outputs, scores of 2 or 1.
So, more good stuff, less bad stuff.
Precisely. They also ran statistical tests, Wilcoxon-signed rank tests, which confirmed significant improvements favoring TablePilot Tuned over both the baseline and the vanilla version. It robustly substantiates that optimizing the ranking via rec-align leads to perceptible improvements in quality as judged by humans. It genuinely feels better to use.
This human-centric validation is incredibly reassuring. It suggests TablePilot isn't just technically correct, it's built to think like an analyst, prioritizing what's useful, clear, and understandable. It really delivers on that human-preferred promise.
It seems so, yeah. The human experts agreed it was better.
Now, to truly understand why TablePilot works so well, the researchers performed an ablation study. That's where you systematically remove components to see their impact, right?
Exactly. It's like taking apart an engine piece by piece to see what each part does.
What do they learn? Which pieces are truly indispensable?
The ablation study was fascinating because it showed the individual contributions. The results, in Tables 4 and 5, unequivocally show that nearly all designed components contribute to performance improvements. It's not just one magic bullet, it's the whole system working together.
Okay, like what specifically?
For instance, removing sampling or explanation, those initial preparation steps, led to noticeable drops in both execution rate and recall. This confirms they're fundamental for preparing the LLM's input correctly.
Makes sense.
Similarly, removing the revision step, that optimization stage, also significantly impacted performance. This proves that the iterative refinement, especially the multimodal part for charts, is vital for accuracy and clarity.
So optimization is crucial.
Definitely. But perhaps most crucially, removing the ranking module entirely led to substantial drops in recall at K across all tasks, like a 13.57% drop in overall recall at 5 without ranking.
Wow, that's a big hit.
It's huge. It underscores that the ranking module with Recaline isn't just a nice-to-have sorting feature. It is a core, indispensable component for delivering those human-preferred valuable results. Without it, you might get lots of technically correct stuff, but much of it would be trivial or irrelevant, leading to information overload. Ranking turns the fire hose into a curated stream.
So this study really reinforces that TablePilot is a holistic system. Every piece is designed to work together, optimizing the whole process.
Precisely. It's a well-architected framework.
Okay, let's bring this all together now with that real-world example from the paper's case study. How does TablePilot actually apply to analyzing something complex like airport passenger traffic data? Walk us through how the framework comes to life.
Absolutely. The case study using annual and monthly passenger traffic stats for major U.S. airports, figures 4 through 11, is a fantastic comprehensive demonstration.
So, step one first, analysis preparation.
Right. TablePilot takes the raw, extensive dataset. First, it intelligently samples it to create manageable subset. Then, it generates that rich contextual table explanation, figure 4. It details each column, airport code, year domestic passengers, and their relationships, like total domestic plus international. That context is critical.
Right. Data prepped. Step
Yeah.
two, module-based analysis.
Exactly. Leveraging that prepared data, it generates diverse tasks. Basic analysis. It might suggest grouping by airport code, calculating average domestic passengers, and sorting figure 10 query 1 result. This immediately shows LGA leads in average domestic traffic, then EWR, then JFK. Quick actionable comparison. Data visualization. It creates insightful charts. That trend of total passengers line chart, figure 10 query 3, vividly shows JFK's steady climb, surpassing others, and EWR's growth. The relative trend stacked bar chart, figure 10 query 4, reveals that growing proportion of international passengers, showing that airport internationalization trend hugely strategic for airports. Statistical modeling. It performs predictive analysis, for instance, forecasting JFK's total passengers for the next 12 months, figure 11, query 5. These projections align with seasonal patterns, lower winter, summer peaks, invaluable for operational planning.
Okay, then step three kicks in, analysis optimization. We saw some examples earlier.
Right. Remember that messy line chart from figure 7 with overlapping labels? TablePilot's multimodal revision recognized the unclear image and corrected the code, producing the clean chart in figure 8 and 10. Visually self-correcting. And it also did content optimization. It replaced that simple data filter query with the more insightful year-over-year growth rate calculation, figure 10, query 2, showing, for example, ACY's 18% drop one year, then a 7% increase the next real dynamic changes.
And finally, step four, analysis ranking.
Yes. The system scores and ranks these refined results. The final analysis report, figures 12-14, consolidates the top recommendations like an executive summary. And crucially, it correctly identifies that regression model predicting total from domestic and international as meaningless because of the inherent sum relationship, figure 9, avoids that trap. The report emphasizes key takeaways: JFK's dominance, LGA's domestic lead, EWR's growth, the volatility of smaller airports, giving a rounded strategic overview.
This case study perfectly demonstrates how TablePilot provides more practical and insightful data analysis recommendations. It really acts like an intelligent assistant, finding trends, highlighting patterns, even pointing out pitfalls.
Yeah, it's about seeing the full picture quickly and accurately, transforming data into real intelligence.
This deep dive has truly shown us how TablePilot marks a significant new milestone. It's a remarkable leap in how AI can assist us in making sense of complex information, moving beyond just presentation to genuine insight generation.
Indeed. The paper concludes that TablePilot offers superior performance in generating comprehensive, human-preferred analysis. But like all cutting-edge research, there are always exciting areas for future work, which the authors discuss thoughtfully in Appendix A.
Always more to do. What's next for this kind of tech?
Well, one area is enhanced data curation. Better, more carefully curated training data could boost performance further. Quality in, quality out. Another is advanced multimodal training. Integrating multimodal DPO, especially for visuals, is a big future step. Imagine TablePilot understanding chart aesthetics even better, critiquing layouts, suggesting alternative visuals based on the data's story.
Wow.
They also plan for expanded analysis modularization. Adding more diverse or specialized modules, maybe for natural language generation to write summaries, or geospatial analysis, or domain-specific things like bioinformatics.
Making it even more versatile.
Right. And a really fascinating direction is evolving towards a multi-agent system. Different modules could interact, complement each other, provide feedback. The visualization module finds a trend, prompts the stats module to investigate, maybe the basic module breaks it down further, much more interactive and intelligent.
Like a team of AI analysts collaborating.
Exactly. And finally, efficiency optimization, making it faster, perhaps replacing some LLM calls with smaller models, or even traditional ML where appropriate, streamlining the process to make it more accessible.
This technology isn't just about faster analysis, is it? It feels like it's about fundamentally shifting the role of the human analyst.
I think so.
If AI can handle the tedious wrangling and initial insight generation, what new, higher-level questions can you, the analyst, start asking? How does this empower innovation and finding solutions previously hidden by information overload? It's really thought-provoking.
It frees up human analysts for higher-level strategy and interpretation, absolutely.
So what does this all mean for you, the listener, right now? How can you start applying these principles of intelligent data analysis in your own work or studies, inspired by TablePilot?
That's a great takeaway question. Here's a practical action plan based on the core principles that make TablePilot so effective. 1. Prioritize data preparation as a strategic asset. Seriously, before you jump into analysis, take time to understand your table. What's the theme? What do columns mean? How do they relate? Think like TablePilot's analysis preparation. Annotate your data, add context. This upfront investment pays off hugely in clarity and accuracy.
Get the foundation solid.
Okay. 2. Cultivate a query code result mindset. For any analysis, frame it this way. What question am I asking? Query. How would I execute it? Code steps. What should the output look like? Results. This structured thinking, core to TablePilot, brings clarity to your own process.
Think it through step by step.
3. Embrace diverse analytical perspectives systematically. Don't get stuck in one mode. Always ask, can this be understood better with a basic aggregation, a visual chart, a statistical model? Practice moving between these modules in your thinking, just like TablePilot does. Get that holistic view.
Don't just make bar charts all day.
Exactly. 4. Practice iterative refinement and self-critique. Don't expect perfection first time. Look at your results critically. Are they clear, insightful, or just meh? If a chart is cluttered or a result feels trivial, refine it. Iterate. Just like TablePilot's analysis optimization, it's key to quality.
Keep improving.
And finally, 5. Cultivate a human preference mindset for impact. When you present data, always think about your audience. Is this meaningful, relevant, reasonable, diverse, interpretable, and insightful for them? That's the essence of TablePilot's ranking. Ensure your analysis is not just technically sound, but genuinely useful and easily understood by the people who need to act on it.
Focus on the end user, the decision maker.
Precisely. That's how you drive real impact with data.
That was a truly insightful deep dive into the world of tabular data analysis powered by large language models. We hope you've gained some valuable nuggets today that will help you navigate your own data challenges with perhaps a newfound clarity and confidence.
Hopefully it provides some useful frameworks for thinking about analysis.
Thank you for joining us today. Visit the AI Coach website for more AI insights.